the lecture number 4, Deep Dynamic Compaction. So throughout this class, we're going to talk about the mechanical modification methods for the deep soil, and we'll talk about how to identify the design parameters of deep dynamic compaction, and we'll learn to describe the quantitative measures of deep dynamic compaction, such as applied energy in effective depths and particle velocity, and to describe the interplays among these design parameters and the soil characteristics. Okay, so let me briefly explain the how the deep dynamic compaction works. So in short, we can call it DCC, and so this is a ground modification technique of densifying soil by repeated dropping of a heavy weight on the ground. So basically it drops the heavy weight on the ground surface, and here in the heavy weight is also referred to as a temper or pounder, and it weighs about 10 to 40 tons depending on the equipment. So the major design parameters are the weight of the hammer or the weight of pounder, and the height of drops, and the spacing. So we're going to talk about the spacing in a minute. So the effective depth by this dropping weight can be calculated by using this equation. So 0.5 times square root of W times H. Here just ignore the unit, but the W is the tons, H is meter, and then you get the effective depth in meter. In DCC, the deep dynamic compaction, you drop the weight in in regular spacing. So it's called the grid and grid pattern, and there's a spacing between this dropped point. So if your weight is dropped here, this from center to center, the interval or the spacing is called the grid spacing, and it's called the S. So the total energy applied by this DCC can be calculated this equation, and here the N is the number of drops, and W is the weight of hammer or the weight of temper, and H is the dropping height, and P is the number of passes, and the S is the spacing. So S square means the unit area between this dropping point. So S is one of the design parameter, so that you can adjust the S to have the optimum number of drops, which is typically people choose to have 7 to 10 blows. So then let's move on to the handout. So please look at the handout. This is the short note about the deep dynamic compaction. So deep dynamic compaction is ground improvement process for compacting and strengthening the loose or soft soil to support the building and structures. And this method involves the systematic dropping of the heavy weight in a pattern designed to remedy poor soil conditions at the proposed building site. In soft ground area, dynamic compaction has proved to be an effective and economical alternatives to preloading and foundation piling and deep vibratory compaction, etc. So the deep dynamic compaction, as you can see from picture, you have a heavy weight or the temper or the pounder, and it just drops it, and normally the height is about 10 to 30 meter high. And after dropping it, so you can see a kind of a hole called a crater. Crater is created. So at the end of the this dynamic compaction, before you completed the project, you have to fill this crater, and then you go through the ironing phase with the lower compactive effort. So dynamic compaction requires the controlled application of dynamic stresses to the ground surface, and the stresses are created by the impact of the heavy steel temper dropped from heights up to 80 feet on a predetermined grid pattern. A crater, like shown in this picture, is formed at the impact point, and that may be up to 8 feet. So it can be like 2 meter or 3 meter deep. And the craters are backfilled by end dumping fill into the craters. Several phases or several passes of the tamping may be required across the site, depending upon the level of improvement required. Following the completion of the high energy tamping, a low energy or ironing phase is performed to compact the material in the craters and in the upper 5 feet of the formation. The ironing phase consists of dropping the weight from a drop height of 10 to 20 feet on closed centers. So this shows the picture of the old, so the deep dynamic compaction has been really old. So it's been, people implemented this technique since like 17th centuries. Okay. Dynamic compaction, again, the dropping of the heavy weights on the ground surface to densify the soils at depths, and Roman used to use the technique heavily, and modern application developed by Menard in France in late 1960s. So the application is to reduce the foundation sediment and minimize the liquefaction potential, permit the construction on fields, densify the garbage dump, improve the mine spoil, induce the sediment in collapsible soils. And the typical parameters is the weight of the 10 to 40 ton, and the drop height is, as I said, like 20 to 30 meter, or 50 to 100 feet. And impact grid is 7 by 7 feet or 25 by 25 feet. So the grid pattern can be like rectangular or the square type, or it could be like diagonal patterns like this. And effective depths, so the depths, the D here in this picture, the maximum depth of the improvement up to 10 meter. And major densification occurs, so within these depths, major densification occurs about half to 2/3 of the effective depth. So here, maybe half and 2/3, 1/2 to 2/3 of the D. In this interval, you have a major densification. The compaction program typically includes the 2 or more steps, or the people call it 2 phases, or the multiple phases, and high energy phases. So you drop the pounders with the heavy weight. Widely separated impact points must compact at depths, typically 7 to 12 drops. So this is the number of drops per drop point. Backfill craters with the surrounding material. So you fill these craters with the surrounding material, and then this will result in loosened surface layer, so that you have to have a ironing pass in between drop points of the high energy phase. So densification mechanism. So it's like the standard Proctor test. So if you have a dry soil, explosion of the air due to impact energy, and if you have a saturated soil, it will be same with the blasting. So you have a induced liquefaction, and it increases the pore pressure, and then water drains, the soil settles at the higher density. So basically, you're shaking the whole saturated soil to pack or to the reoriented particle in a dense state. And collapsible soil. For the collapsible soil, weak cementation is broken by impact energy, so this metastable voids will collapse. So if you have this kind of a weakly cemented with a large void, then when you apply the energy, this soil will become collapse, and it's gonna be more dense. after the collapse. So saturated fine-grained soil dynamic consolidation, and this is a kind of very difficult technique. So both successes and failure reported. Improvement obtained by reduction of the volume of air bubbles and water drains through fissures and cracks generated by impact. The advantages and disadvantages of this DCC. Advantages: feedback on the ground condition, but it can induce the vibration, so pros and cons. For the pros, densification can be observed as the work proceeds and can be used in highly heterogeneous soil, like landfills or the garbage dump, and creates a uniform bearing stratum. Densification can be achieved below the water table, but the non-specialty contractor can perform the job because it's simple. But the cons are: to prevent the surface softening, groundwater table should be located more than 2 meters below the ground surface. So if the groundwater table is too high, then it will be difficult to apply this technique. And maybe a working platform for moving equipment in a very soft soil could be so if the soil is too weak, so that when the equipment is placed on the soil, that it can also settle down. So you don't want to have your equipment to be like buried in the mud. So you need some working platform, especially when you have to move the equipment. A lateral ground movement can occur up to 6 meters from point of the impact. So if you have this kind of excavated site, and when you pound it with the DCC here, then you have a lateral movement of the soil, and this can damage the surrounding material or the structures utilities. So typical ground response. This graph shows the typical ground response with time after successive coverages of the dynamic consolidation. So basically you are applying the impact here and here and here, and when you apply the impact, the volume reduces, and at the same time, because of the impact, the pore pressure increases. So the pore pressure increase to 100% means that the pore pressure becomes the same with the effective stress. So it became liquefied. The soil is liquefied, and then this liquefied soil just settle down as the water drains out. Then the volume decreases like this. And as the volume decreases, as the pore pressure dissipates, the bearing capacity increases. So bearing capacity here, the first drop is here, and after the second drop, it slightly increased, right, by this much. And then the third drop, so it also increases a little bit. So bearing capacity keeps increasing gradually with the consecutive tamping. And applicable soil type. So this graph also shows that the applicability of DCC. So zone 1 is the most appropriate zone. So the part, when you look at the grain size, it's mostly sand, and the plasticity index is almost 0. So this is in the for the sandy soil, you can apply the DCC very effectively. But for the clay and the fine-grained soil, if the soil is impervious and the plasticity index is larger than 8, then it's not recommended to apply this DCC. It's not recommended. In zone 2, it's kind of a transition zone in between zone 1 and zone 3. So it can be a good but it's not like as effective as in the sandy soil. So the summary is expected DCC result. Depending on the ground type, the effectiveness varies. So sand, you have excellent effectiveness. The silty sand is good, and silty is fair, and clay is poor. So here is about the maybe like zone 1, and this maybe zone 2. This might be zone 3, the clay soil. And also some dumped fill and mine spoils and garbage can be categorized into zone 2 or zone 3. And suitability of the deposits for dynamic compaction. So this is basically the same duplication. So you can read this table and it summarizes the applicability of the DCC. Very good. Okay, let's go through the development of design plan for the DCC. So the main design parameter will be the weight of temper and the dropping height and spacing and number of drops and number of passes. So these are the procedures for the design, and you perform the site investigation first and determine the project performance requirements and selection of the temper and the drop height, and applied energy should be determined, and then you confine the area to densify and determine the spacing and number of drops and establish the number of passes. Then you design the surface stabilizing layer like the ironing phase. Then you develop a plan for the quality assurance and the quality control. So move on to step 2. You determine the project performance requirements. So this shows that the SPT N value after the DCC. So after DCC, if the previous coarse grain soil is your soil, then the SPT value should be about the 40 to 50. This is the upper value, the maximum test value. And the semi-pervious, then you have different value. And if you're using CPT instead of the SPT, so this is the SPT and CPT, then it shows the kind of a criteria value for the reference when you do the quality assurance or the design the DCC, the deep dynamic compaction. So then the step 3 is select a temper and the drop height. So this graph shows that the y-axis is the depth of influence. So the effective depth here, D, and the x-axis is the energy per drop. So this is a square root of W times H. So square root of W times H. And you can see that the data points are quite linear. So it has linear relationship between this D and the square root of WH. So based on this finding, people developed this kind of empirical equation with the empirical coefficient N. So here the D is in meter, W is in tons, H is in meter, and the N doesn't have a dimension, and it varies between 0.3 to 0.7. So the effective depth also depends on the soil type, drop method, and temper area, and total energy applied, and the presence of the energy absorbing layers, and presence of the harder layers that bounce back the energy. And N is quite specific, the site specific, so you have a different N for different soil type and different sites. Typically, people use the 0.5 for the pervious soil, like sandy soil, and people use the less than 5, like around 4.4 for the semi-pervious soil. So N can be determined from carefully conducted tests, and Lee and Guo also did some research about this, the effective depth. These studies are based on the Singapore data. And the influential area or the depth of influence is also affected by temper area. So if your temper area, let's say that this is the square and this is the side view, as the width gets increased, then you have effective area like this. Then the effective depth decreases as W increases, but the radius of influence area increases. And this temper can have different shape, like it can be rectangular or it can be circular. So there is a optimal temper radius R naught, for a given energy per drop and the desired degree of improvement. The next step is to determine the applied energy to achieve the required depth of improvement. And the applied energy can be calculated using this equation, as we saw in the previous note. Here the S is the spacing and N is the number of drops, and H is the drop height, and P is the number of passes. And so for the zone 1, for the sandy soil, where this DCC is very effective, the applied energy is about 20 to 25 ton times meter per cubic meter. I think it should be a square meter, because we are dividing with the area. Oh, no, it's okay to have the volume. No, it's okay. I think they divided with the volume, the thickness, sorry. And the length, the semi-pervious fine-grained soil for the zone 2 is a little bit higher, so 25 to 35. And for the zone 3, it's not applicable, but the landfill has much higher energy, specific energy applied. To get some feeling, the energy value, how big is the value is, standard Proctor test applies the energy equal to 60 ton times meter per cubic meter. So you can see that if you apply the DCC for the landfill, the applied energy will be pretty much similar to the standard Proctor test. Use this table only as a guide, and more energy to deposit with the low initial relative density. And also you have to keep in mind the densification target and penetration values and the SPT value and CPT values. Then the next step is to select the project area. So if the area is like this hash sheet, your target area to densify is this hashed area, then you extend for the DCC technique to be applied by the distance equal to effective depth. So that if the target area has length, then you will apply this the DCC, the deep dynamic compaction method for the L plus 2D. So you have to have some margin not to affect the surrounding structures or surrounding utilities. And when you know the location of the footing, so you know the location where the footing will be placed, then you can apply the additional energy to footing location so that you have a better densified soil. Then the next step is to determine the grid spacing, S. Typically, the grid spacing is determined as 1.5 to 2.5 times the diameter or the width of the temper. So S is about 1.5 to 2.5 times D. If the D is the diameter of the temper. In semi-pervious soil, use 2 or more phases with the time lag to cover each pass. And also, if the number of drops is less than 7 or larger than 15, then you adjust the S. To have the number of drops in between 7 to 15 or 7 to 12. This is a very interesting figure. So the axis is the x-axis is S over D. So distance, S is the spacing, and D is the temper diameter. So as you go to right side, the spacing is getting bigger, and the y-axis is the friction angle. So here the delta pi c is the increasing friction angle at center of the grid, further away from the dropping point, and delta phi sub b is the increasing friction angle at drop location. So the friction angle increases at this location. So when the spacing over D is less than 2, so then it quite homogeneously densified, so that you have pretty much the same friction angle increase. But as the spacing gets bigger, so that you have a wider spacing, then this decreases linearly with the S over D. And this friction angle was determined from the cone resistance from the CPT using this Meyerhof equation. So using this kind of a concept, you can see that the why the people recommend the S over D value between 0.5 to 2.5. So I think this recommendation is from this graph. And the step 7, establish the number of passes. Actually, this is limited by the depth of crater, because if you increase the number of drops too much, and if you do the passes, increase the number of passes, then you can create this kind of a crater. So you have to stop if the ground heave occurs. Wait until the pole pressure dissipates. So depth of crater should be less than the height of the hamper plus 1 feet. So this graph shows the crater depth divided by the square root of the WH, and this is the number of drops. And as you can see, as the number of drops increases, so you have a deeper crater. I think this graph shows much clearer. So number of drops and the crater depth, and as the number of drops increases, so you have a deeper craters, and you don't want to have too deep craters. Okay, let's move on. So then finally you design the surface stabilizing layer. So you have to backfill the craters, and then you apply some fill less than 1 meter and do some ironing with the shallow compactor. For this ironing phase, you can use the coarse grain granular material, gravel, crushed rock, and the building rubbles. And then for the quality control, the vibration should be measured. So because if the vibration is too high, that means that you are dropping the height, dropping the weight too high or too heavy, then it can cause the severe vibration and disturbance to the neighbors. So typically the vibration frequency is about 5 to 12 Hertz, and at this frequency range, damaging old residence occurs at 30 mm per sec of the particle velocity, or 90 mm per sec for the modern residences. So if the vibration goes through the ground, you can also install the custom trench to block the vibration going to the residential area. So like this. And for the quality control, okay, let's look at this graph first. And this shows that the energy factor, so energy versus the particle velocity. So it says that 0.7 inches per second or 0.5 inches per second is will cause the damage in the older and modern residences. So 0.5 is here, which is very disturbing, and larger than 1 is very disturbing. It's fairly disturbing, and strongly perceptible means that the people can detect, or people can feel the vibration from the DCC from the distance, and distinctively perceptible and slightly perceptible. So I think that it's recommended that it has to be lower than the 0.1 inches per second. So that's about 2 millimeter per second, 2.7. So this is around in millimeter per second, 2.7574 millimeter per second. And for the quality control, you can measure the surface sediment, and also you can perform some in situ testing like SPT and CPT and PMT. Also, you can monitor the pore pressure dissipation when there's a clay layer. This is a very good table showing that the cost of each method for the soil improvement. So you can see the dynamic deep compaction and vibral replacement, vibral compaction, excavate and replace, and grouting, chemical grouting, jet grouting, and this is the cost per cubic yard. And you can see that the deep dynamic compaction is pretty cheap comparing to the other chemical injection method here in the compaction grouting and jet grouting. Interesting thing is that among these three methods, chemical grouting, compaction grouting, jet grouting, and freezing, see that this compaction grouting is the most cheapest one. And these are the references for dynamic compaction, and I recommend you to read these papers. So to wrap up this class, we talked about the design parameters of the DCC, like spacing and WH, and the number of passes, number of drops. And we also described the quantitative measures for the quality assurance, effective depth and particle velocity and SPT value, and also we can calculate the applied energy from the given geometry. And we talked about how the temporal width affects the effective depth, or the permeability of the soil, whether it's a sandy soil or the silty soil, the clay soil. The permeability of the soil affects the effectiveness of the DCC. Okay, that will be the end of this lecture.